Hello, everybody. Thank you, Tony. Welcome. I'm just going to turn my camera off and then we'll get into this. So, HS2, it's Britain's new high-speed railway, and it will be the backbone of our rail network, carrying over 30,000 passengers a day, connecting 30 million people and 8 of our largest cities. When completed, 345 miles of brand new high-speed track will run between Birmingham, Manchester, Leeds and London. Our trains will also run on the existing network and serve 25 stations from Scotland to the southeast. This is a huge undertaking, Britain's first new intercity railway north of London in 100 years. Europe's largest infrastructure project. This presentation focuses upon the underground construction elements allowing HS2 to traverse the complex topography of the UK. So this is the main route diagram, dark blue being phase 1, which is currently in its construction phase. This phase is 230 kilometres, of which about 25% of it is in tunnels. I will primarily talk about this section today. The light blue section and yellow section is phase 2 and is within its development phase. Later, I will give a summary as it stands for these tunnels in this section. HS2 phase 2B comprises 2 parts, the eastern leg and western leg. The eastern leg runs from the West Midlands to Leeds with connections to the Midland Main Line, East Coast Main Line, and the western leg runs from Crewe to Manchester and will also join the West Coast Main Line. In total, phase 1 and phase 2 consists of approximately 555 kilometres, that's 345 miles of track. 62 kilometres of this is in twin bore tunnel and 9.6 kilometres is in a cut and cover tunnel. So, tunnelling and underground structures. Primarily, 2 different tunnelling techniques are used to construct the main running tunnels for HS2. 2 techniques are shown here, with a possible 3rd technique in some locations. The first technique is a green tunnel, also called a cut and cover tunnel. The second construction technique is a bored tunnel, and this is the most extensive method used on HS2. Tunnel boring machines are used to create these tunnels. The third, less common method, which not shown here, is a mine tunnel using sprayed concrete linings, although this technique is used extensively for the cross passages connecting the 2 running tunnels. All the tunnels have varying dimensions, the largest 9.1 metres as shown here, which is the Chilterns Tunnel and is the same height as 2 London buses stacked on top of one another. Here's a comparison to other well-known major tunnels in the UK. Going back to the green cut and cover tunnels, the trench is excavated using a typical open cut method, which has inclined batters to the sides, particularly used in the more rural areas of HS2. Alternatively, on the right, in urban areas, a retained cutting is used which consists of piles of diaphragm walls to create the side walls. Once the roof or temporary propping has been installed, the main tunnel profile is then excavated and the base is constructed. Here's a finished green tunnel on High Speed 1 through the Kent countryside to give you an idea of how that will look. So, working from south to north, along the alignment of the route, I describe all the tunnels we have on HS2 phase 1. First, we have the London tunnels. The first tunnel being the Euston Tunnels, 2 TBMs are driven 4.5 miles or 7.3 kilometres towards the new Euston Station terminal from the Old Oak Common Traction Maintenance Depot, which is to the west of London, approximately 1/3 of a mile south of Willesden Junction Station. Just prior to the train exiting the tunnel at Euston Station approach, there will be a large cavern to enable the lines to split a total of 3 tunnels with 3 portals in the vicinity of Mornington Street Bridge. The cavern makes it possible for the inbound tunnel to divide into two. This cavern will extend from just north of the Oval Road, Gloucester Road Avenue junction, to a short way south of Parkway. The cavern will be created under the existing Network Rail tracks. From the same launch location at Old Oak Common, a further 2 TBMs will be driven 3.4 miles, 5.6 kilometres north towards Green Parkway shaft. Norfolk, these are called Norfolk Tunnels East and located at the end of Rockwell Avenue next to the Royal Mail Greenford Mail Centre and the IBM Greenford. The final 2 London TBMs are driven south from West Ruislip, south of the Ruislip Golf Course towards the Green Parkway shaft again, where they will finish their 5-mile, 7.8 kilometre journey. And at this location, all of those 4 shafts, TBMs will be removed from this shaft. All these tunnels run an average depth of 35 metres below ground, 25 metre cover from the crown of tunnel to ground level. Next, I'll show a video of the status of these tunnels.
We are currently in West Ruislip Portal, which is in the northwest of London. This is the portal site for where the trains from the north and the Midlands come into overground and go underground for 13 miles into Euston. What we've done in the last year or so is mobilise everything, so build haul roads, drainage, everything that you need to do to get ready for the permanent side of works. And in the next couple of years when we start launching TBMs, we've got to do quite a hefty amount of piling, sheet piling and board piling. There'll be a lot of reinforced concrete works for the walls, the base slabs and stuff of those sorts. There'll also be like a launch chamber that will need to be built for the TBMs to drive off of. Working on it for SDS and the HS2 project offers me lots of opportunity to expand my range in where I want to go with my career. Lots of development, lots of opportunities. Yeah, it's just a great place to work.
So, the next tunnels we have next along the alignment is the Buckinghamshire tunnels. 2 further TBMs here will drive northwest 10 miles or 16 kilometres from south of the M25 between junctions 16 and 17 at Chalfont Lane. This being the longest single board tunnel and largest of tunnels on HS2. Up to 90 metres deep, the tunnel goes beneath the site of Special Scientific Interest, SSSI. This tunnel runs an average depth of 44 metres below ground, 34 metre cover from the crown of the tunnel to ground level. Wendover, just north of this one, is the first of 3 consecutive green tunnels, all 3 constructed by open cut methods. Along this section of the route, at 0.9 miles or 1.2 kilometres long, this tunnel runs just below the surface with minimal cover. Next is a video of works being currently undertaken for the Chilterns Tunnel at the M25 Portal site.
I'm 24 years old. I've been with the line now for 5 months. And before this, I was working in Australia, and before that, I was working at Hinkley Point C. We're on the HS2 C1 site, just next to the M25. So as you can see, we're building the South Portal. These concrete slabs effectively form the base of where our tunnel boring machines will sit. The TBMs will then start their 10-mile journey from the South Portal, breaking through to the North Portal. It's a hugely exciting project. I mean, the scale of it is massive. Really exciting, really, practically it's really interesting, and yeah, I hope to go on to many more projects.
So now we move further north to the Warwickshire and Northamptonshire tunnels. Here, the next 2 consecutive green tunnels in Northamptonshire, both tunnels are approximately 1.5 miles or 2.5 kilometres. Greatworth Tunnel runs just north of the village of Greatworth, and then next Chipping Warden passes between the villages of Astonley Walls and Chipping Warden. Both are required to eliminate deep cuttings and reduce the impact on the villages, therefore enabling the ground profile to be restored so it blends into the original landscape. The ground cover on these vary from very shallow to a depth of 14 metres. Next, the Long Itchington Wood Tunnel at Bascott Heath near Southam, Warwickshire, is another bored tunnel required to allow the route to pass beneath another site of special scientific interest, SSI. At the southern end, the construction will be cut and cover tunnel for approximately 0.1 of a mile, followed by the bored tunnel construction for approximately 1 mile or 1.5 kilometres. The cut and cover section is required for the construction through the current alignment of the A425 Leamington Road and part of the Dallas Burston Polo Club site to the north. Next video is describing the works currently being undertaken for the Long Itchington Tunnel at the Welsh Road compound in this location.
We're constructing a twin-bore segmental line tunnel, so which means we'll be launching a tunnel boring machine from this site here to protect this woodland, what you see behind me. Okay, we need to protect these trees and protect these habitats. And that means we need to protect the tree roots as well. So we need to make sure that we don't influence the trees by damaging the roots. It was really challenging to coordinate with the design teams and the environmental agencies. We're constructing a twin-bore segmental line tunnel, so which means we'll be launching a tunnel boring machine from this site here, 1.5 kilometers. It's such a great project. It's a big project. There's a lot of attention and there's a lot of opportunity for development. And the works that we're doing here will last for the next 120 years. It's amazing, it's majestic, and this is why we are here.
Okay, so now we come towards the end of the phase 1 part of the route towards Birmingham. These are the West Midlands tunnels. First we have Burton Green Tunnel, which is a green tunnel allowing the route to pass between the city of Coventry to the northeast and the town of Kenilworth to the southwest of the route. At this location, the route utilises the railway cutting of the former London and North Western Railway Berkswell to Kenilworth branch. The railway was closed to traffic in the 1960s and is currently part of the Kenilworth Greenway. Due to proximity of this tunnel to buildings, the construction cannot be undertaken using the open cut methods previously shown. Here, the walls are constructed using diaphragm wall methods. Further north, the line enters the Bromford Tunnel on the Birmingham Spur for 3.5 miles, 5.8 kilometres. This tunnel is required to allow the route to pass underneath the Bromford M6 motorway viaduct and a nature reserve at Park Hall on the eastern edge of Birmingham. This tunnel is the smaller size of 7.55 metres due to the train slowing to eventually reach the Birmingham Curzon Street station terminus. So here's some facts that I've described. So a little summary. There's some 114 cross passages to connect the two twin bore tunnels together, and plus over 6 million metres cubed of spoil to be excavated from the tunnelling operations. Working further north just giving a brief overview of the future phase 2 tunnels to be constructed. These are still under development, but a total of 16 kilometres more of twin bore tunnels. So that's, with a twin bore tunnel, that's 32 more kilometres of tunnelling to be undertaken. Two of the major tunnels within this phase 2 will be the Manchester, part of the Manchester tunnels on the western leg, and the 3.8 mile Crewe tunnel, which has 2 ventilation shafts, and the 8 mile Manchester tunnel has 4 ventilation shafts. The tunnels on HS2 traverse the UK from south to north, as we've shown. This means that the tunnels capture varying geologies that are apparent in England. The strata crosses a lot of southern England dip towards the southeast, with younger strata laying on top of older ones, as identified in this table. So the London clays from the London region moving up towards mudstones in the Midland regions. And these are the phase 2 ground conditions, which are prominently mudstones and sandstones and coal measures, and they're more common as the route progresses north. So, moving on to tunnel boring machines. We'll have 10 of these on the first phase of the project. Just a little video to give you an idea. So here's the TBM long section. This is the Chilterns Tunnel TBM. At the front is the main element that most will be familiar with, the main TBM shield with the cutter head. However, there is much more to a TBM. The TBMs, as been said, 170 metres in length, nearly twice the length of a football pitch. Each one weighs roughly 2,000 tonnes. When they start, they will run non-stop for 3.5 years, only stopping for Christmas and bank holidays until the tunnels are complete. The tunnels will go as deep as 90 metres below the ground, ensuring communities and countryside above are not impacted by the railway. The size of the TBM cutterhead, which will bore the tunnels, is 10.26 metres. To the rear of the TBM shield, an erector arm with a segment erector will lift each of the tunnel lining concrete segments into place as each tunnel ring is built. It can rotate into position 360 degrees. The tunnels will be lined with concrete segments that will be about 2 metres by 4 metres and weigh on average 8.5 tonnes each. 112,000 of these concrete segments will be required to complete just these tunnels on the Chilterns. Is a little bit about the these TBMs.
So in this section, we're building a 16-kilometre tunnel for HS2. The construction method is a tunnel boring machine of a variable density type, the first that's ever been used in the UK, and it's probably going to take roughly 3 years for the excavation to be completed at roughly 15 metres a day. Tunnelling is a hazardous environment, so anything we can implement to avoid accidents from occurring, it's always a good plus on a project.
We are in fact using our own experience and our own lessons learned on the various projects before to try to improve the specific area where we found that our people were maybe more at risk.
The two areas that we have looked at are the removal of wood spaces from the ring sections in the tunnel and the placement of dowels.
These two issues have some inherent safety risks that we want to try and avoid. So as a contractor, we've come up with a robotic solution to sort of mitigate these two risks. This robot is installed on a trolley behind the segment crane that is picking up the segments. As the segment crane moves forward, this robotic arm follows behind it automatically. So the first piece of equipment is the doobie-doo part of the robotic arm. This doobie-doo picks up a dowel and installs it straight onto the segment. This is an automated process, so he picks up one dowel for the one side and then one dowel for the other side.
The wood spaces are used to stack the ring segments in the yard, but are still in place when segments are brought inside the tunnel for installation.
The second part of this robotic arm is the crocodile innovation. Essentially, the robotic arm moves backwards as the segment has been loaded onto the segment feeder. This piece of equipment is essentially a claw, which drags along the top of the segment that had the pieces of wood left on top. As it drags it across and meets the second piece of wood, the claw closes. The robotic arm can then pick up the pieces of wood that have been left over.
I think everybody is quite excited about this innovation because it was teamwork, and I think it's really a good innovation to share with other partners or contractors to be sure that on all these projects in HS2 we are working in safe conditions.
Everything we do, we're always looking at the problems and looking at how we can improve on them. Even if they're already safe, we try and strive to make them safer, trying to avoid putting people into harm's way if we can. And that's just typical of how we design our TBMs.
This crocodile innovation is an illustration of what are the values that we want to implement here on C1. We did a lot of works, all the team together, to establish common values between the client, ourselves, the supplier, to be sure that all the people involved in the project are buying this value. And the best example to, I would say, achieve the first one is to achieve a proper safety on site, is to demonstrate it through this type of innovation.
So, the twin bore tunnels. Two bores are commonly provided for safety. If there's a fire in one tunnel or an incident, then the passengers can be disembarked onto the emergency walkway and enter the cross passages through automatic sliding fireproof doors into the other bore, which acts as a place of relative safety. At this point, a rescue train can be safely sent to the safe bore to rescue the passengers. During the time of evacuation, tunnel ventilation will be operational in order to form fresh air pockets and protect the passengers from smoke. Typically, 7.55 metre internal diameter, or ID, tunnels allows train speeds up to 230 kilometres per hour, or 143 miles per hour. The larger 8.8 metre ID tunnels up to 360 kilometres per hour, which is 225 miles per hour, and the largest on the Chilterns, the 9.1 metre ID tunnels for long tunnels up to 360 kilometres per hour. Where additional gross-free areas are deemed necessary in the design, the chosen tunnel diameters allow pressure variations within the tunnel and train to be controlled for passenger comfort and reduce the impact to micro pressure waves on neighbouring communities at the tunnel entrances and exits. This is an image of one of the tunnels on High Speed 1 in Kent. A little bit on tunnel advance rates. Common questions: how fast do the TBMs bore? Bored tunnels built up the two main activities: boring, which is the instantaneous advance rate, and ring building, which is segment building to form the tunnel lining, both bounded by the red box shown here. Both activities are less than 50% of the short-term advance rate due to other factors called utilisation factors, like routine maintenance, temporary track laying, and pipe extensions that are required to enable the TBM to continue. The long-term advance rate is usually further reduced due to project-specific delays, which there will be numerous on any project you have. For instance, traversing a TBM through a shaft location or creating some of the cross passages that I've shown, if they're simultaneous to the tunnelling. So bearing in mind these different types of advance rates, colour-coded the same. So this slide summarises the possible advance rates that may be achieved on a typical tunnelling project using modern TBMs. Faster, more efficient tunnelling is developing continuously. This next video demonstrates the achievements being made on this project. I'll show that later. So other effects of tunnelling, which is volume loss percentages. When a tunnel is constructed, the ground moves to the excavation face. This results in relaxation ahead and around the tunnel, which propagates towards the surface. A shallow depression or trough results following the alignment, also called ground settlement. Volume loss is the parameter typically used to assess the performance of ground movement from tunnelling, and it is defined as the volume of ground loss of a proportion to the final tunnel volume, and is measured in the plane of the tunnel. Closed face tunnelling is a method where the excavated tunnel face is retained by pressure applied by compressed air slurry or excavated material. The pressure is commonly maintained using a TBM with pressurized chamber at the face sealed against the tunnel lining. This method enables volume losses to be kept minimal. This timeline of project design volume losses and typical volume losses achieved with close-face tunnelling machines from normal running indicates that over the years volume loss is reducing, hence the settlement effects also reduce, thereby enabling these tunnelling projects to go beneath lots of buildings with minimal effects. In order to ensure that the volume losses are controlled, we have extensive monitoring, and it's required above the surface and below the surface to ensure that the methods are working as we plan. Quite extensive list of requirements there to pick up various displacements, strains, and pressures. Another common question is about ground-borne noise. Improvements in rail tunnel performance are shown here with respect to ground-borne noise from railways in tunnels with time. Since each tunnel affects a large number of properties, the value given is only approximately. The figures show the date of opening for each tunnel and the noise level in a building above it. Points 1, 2, and 4 represent recent measurements taken for older tunnels. The introduction of environmental impact assessment process in 1988 is shown by a blue line. The information here shows that the ground-borne noise from tunnels built more than 100 years ago is sufficiently loud to cause complaints. However, more recent rail tunnels have achieved much lower noise levels where the use of mitigation has been justified. Just a final video to show about where we are with the TBMs. So moving on, ventilation and intervention shafts. Below ground level, ventilation shafts will reach down to the twin tunnels below, with fans and other equipment designed to regulate air quality and temperature in the tunnels, remove smoke in the event of a fire, and provide access for the emergency services. On Phase 1, there are a total of 12 shafts and a possible 6 shafts on Phase 2B. London tunnels have 5 shafts. These are Adelaide Road, Canterbury Works, Westgate, Green Parkway, Mandeville Road and South Ruislip. The Chilterns Tunnel has 5 shafts. These are Chalfont St Peter, Chalfont St Giles, Amersham, Little Missenden and Chesham Road. This one's not a ventilation shaft and only acts as an intervention. Bromford Tunnel on the West Midlands Tunnel only has 1 shaft at the Castle Bromwich Business Park. All shafts will have a head house building at the top. None of the cut and cover tunnels have shafts due to their relatively short length. Shafts are typically spaced to a maximum of 3 kilometres. For longer tunnels, they also may get used for TBM inspection when passing the shaft or for retrieval in order to allow the TBMs to drive shorter distances, hence like the one at Norfolk, whereby the Green Parkway shaft is used for this. These shafts may need to be slightly larger for this temporary purpose. Here's some shaft sinking methods. The first 3 are the most common used on the HS2 project due to the size of the structures: diaphragm walling, secant pile walling and contiguous pile walling. And these are some of the pictures of some past projects of what our shafts will eventually look like. So these are some of the developing models of 2 of our shafts, one at Canterbury Works shaft of the Euston Tunnels and one at Mandeville Road of the Norfolk West Tunnels. Most have adits at the track level or tunnel crown level to provide the ventilation flow into the tunnels. Typically, these tunnels are constructed using mine techniques and spread concrete linings. The depth of the shafts are normally deeper than the tunnel, since the shafts are located at the low point of the tunnels, whereby a sump will be located to capture drain water from the length of the tunnels. This is the Canterbury Works ventilation shaft. It is one of 2 shafts on the 4.5-mile Euston Tunnel, located near to London Underground's Bakerloo Line, Kilburn Park train station. Most of our shaft head houses have low maintenance green roofs, as shown here. The design is chosen to blend into the landscape. This shaft head house is in a suburban setting. Chalfont St Peter's ventilation shaft. This is the developing design model of the shaft. It is the second of 5 shafts on the 16-kilometre Chiltern Tunnel and is the deepest on HS2, approximately 65 metres deep. This shaft head house is designed to blend into the more rural landscape. This will be very similar to the next shaft design at Chalfont St Giles. So this is set back from the road. The single-storey building will be wrapped in a simple grey zinc roof with doors and vent openings picked out in a dark bronze colour to provide contrast. Taking its inspiration from the local style of local barns and other agricultural buildings, the head house is designed to fit into the surrounding landscape. The pre-weathered grey zinc roof will age naturally over time without loss of robustness or quality, while the whole structure will sit on a simple dark blue brick base. Amersham ventilation shaft is the 3rd of 5 shafts on the Chiltern Tunnel, set in the middle of a road junction just out of town. The circular single-storey building will be surrounded by a spiral-shaped weathered steel wall designed to echo the shape of the site and the natural tones of the surrounding landscape. Below ground level, an 18-metre deep ventilation shaft will reach down to the twin tunnels below. Robust and durable weathered steel facade fades naturally over time to a dark brown colour in order to let light through. The upper parts of the wall will be lightly perforated with a pattern inspired by the woodland foliage. Little Missenden ventilation shaft is the fourth of 5 shafts on the Chiltern Tunnel, set back from the main A413 and very similar to the Chalfont St Peter and Chalfont St Giles shaft head houses. I've shown 3 work in progress design models plus 4 finalised architectural designs of the ventilation shafts. Look out for news on the chosen design of the other 5 shafts in the coming months. Moving on to sprayed concrete linings, or sequential excavation method. A sprayed concrete line tunnel, or SCL for short, is a tunnel constructed using open face excavation techniques and with a lining constructed within the tunnel from sprayed concrete to provide ground support, often with the use of additional ground anchors, bolts and dowels as appropriate. It's also known as a sequential excavation method, SEM, where open face techniques are used in a sequential process, slowly creating the tunnel in stages. Sprayed concrete is commonly used for substances applied via pressure hoses. Sprayed concrete is concrete conveyed through a hose and pneumatically projected at high velocity onto the surface. Sprayed concrete undergoes placement and compaction at the same time due to the force of which it is projected from the nozzle. It can be impacted onto any type or shape of surface, including vertical or overhead areas. It then requires liquid accelerator to be added at the nozzle to initiate the fast-acting curing process. This is a long section showing the sequencing, showing the alternating elements of the sequence. Moving on with more sprayed concrete line tunnels, we have the 3 tunnels towards Euston Station, which are required for grade separation, as shown on the left, to enable the passage of the downline tunnel over the upline tunnel, and to minimise the gradient on the approach track work to Euston Station. This also allows the upline tunnel to split prior to Euston Station approaches, which is a constrained site serving 11 platforms. In order to achieve this cavern is shown in blue. A little bit more detail here. This is the largest mined underground structure on HS2 using SCL. The Euston Cavern, shown in blue again, and shaft, shown in red and green, is located on land between the existing network rail lines and the retaining walls of the Park Village East Highway. To enable the cavern to be constructed, construction of the Park Village East access shaft, the crosscut and the binocular tunnels are required. This work involves the construction of complex underground tunnelling works in close proximity to a network rail operational railway and associated assets onto Euston, LU tunnels and other sensitive third-party infrastructure. This is zooming in even more. The crosscut, which is a cavern in its own right, is driven out from the shaft, as shown in purple. It is approximately 15 metres high, and this crosscut enables the small overlapping drift tunnels to be constructed perpendicularly. Once they are eventually excavated and filled, they will create the lining of the very large cavern. Moving on to our porous portals. So noise can be generated at exit portals of the tunnels due to the pressure waves created inside the tunnel as the train enters the tunnel at speed. This is well known, understood fact and is mitigated by appropriate design and construction techniques called porous portals. So the design of the tunnel portals, tunnels and vent shafts, where required, will control and reduce in-tunnel pressure waves to assure passenger comfort. Tunnel porous portals play a large part in this, largely to avoid any significant airborne effects caused by the trains entering the tunnel. So these are artists' impressions to show how the porous portal hoods might look in practice. They form a natural extension of the tunnel, and most will partially be or wholly hidden in cuttings. The holes in the roof of the wall are according to local conditions that doesn't affect the performance. You might notice that we have hands hoods on both tracks. So it's not only on the entrance of the tunnel, but also at the exit. And that's because HS2 is designed to be capable of running in either direction, obviously mainly for maybe emergency situations and maintenance. This is developing design of a porous portal hood on the green tunnels in Buckinghamshire and Northamptonshire. Another view of this showing holes in the porous portal at the top right of the picture. And that completes my presentation on the main elements of HS2. I hope you've found this interesting, and if there's any questions. Hello.
Can you see the questions, Andy?
Yes, got the questions. Sorry about that.
Yeah. Okay, great.
So if I work from the top, how close is the Bromford section to the motorway there? So it runs between junction 5 and 6, I think it was, and it runs parallel to it for a bit at junction, that would be junction 6, and then it, if you notice, the M6 viaduct skews a little bit, and it's at that point we pass underneath, and then we're on towards the north of the Bromford Viaduct. So it's quite, it's obviously underneath at the crossing point, but it's within say 20 to 50 meters at varying locations along that route. So there's quite an extensive assessment to do on that viaduct over about a 1.5 kilometre length until it sort of spurs away to go south. Next question. What proportion of the tunnel mileage is for environmental green tunnels, as this is distinct from structurally required tunnels? Total of green tunnel mileage. Total tunnel mileage is for environmental green tunnels. So it's environmental green tunnels work out to, I think, about 5%, around that point. I've previously said 25% was in tunnelling, so around 20% of that is the deeper bored tunnels. Used in meters, yet the preceding slides were in miles. Can we not settle upon metric units? Yeah, unfortunately we do have to use miles on a lot of our corporate data that we pass out, because that's a request. But yeah, that's why I gave it in both units. How hot does it get behind the tunnelling shield while it's in operation? It can get very hot, but obviously on a smaller diameter tunnel, but these are much larger diameter tunnels with much more state-of-the-art ventilation design. So these won't be as hot as other tunnels can be during construction. I don't have actual figures, but hopefully that gives you an idea. Elon Musk has a venture that believes it can achieve tunnelling speeds that are significantly faster than current engineered permits. Do you think venture goals will succeed in this regard? So yeah, this has been at the forefront. We've got the British Tunnelling Society have been working to reply to these reports, and yes, there are other developments. Obviously, each project is different. As I've mentioned, there's various delays. If you're just doing a single tunnel with no cross passages, no shafts, then yes, you will get faster tunnelling. But there are also other TBM developments. One that we're looking at with the Chilterns, which is enabling ring building to be undertaken as the boring continues. So as I showed there, 50% was tunnelling and boring, and then 50% ring building. So it's almost combining them, so making that element 50% quicker, because you're doing them both at the same time. So yes, in part, the whole process might not be 50%, but there are some elements that we can start to make these processes quicker, which is being developed. What is done with the extracted spoil? Most of the spoil will be reused. It obviously has to be treated and separated. So we've got lots of environmental bunds that be made. So depending on the quality, it'll either be used for creation of the embankments along the route, or the environmental bunding that's required along the route that's not required structurally. So it depends on the quality of whether it can be used for a structural fill. Would it be possible for subject to visit some of the works? Obviously, visiting is restricted on some of these sites, but obviously that can be discussed in the future. Will visits for underground, same question. Obviously, there are restrictions on entering the tunnels due to safety requirements and needing enough safety equipment for the workers. It is a confined space, so we'd have to get back to you on that one. Will the signals for the route be in cab bearing? Unfortunately, that question's out of my expertise. We have a whole team on rail systems track personnel who would answer that. Obviously, lots of that is still being developed in parallel with the works. Is there a HS3 planned? So HS3 is, I think, normally, historically, it's been interpreted as being part of Northern Powerhouse Rail, which is linking your Manchester to Leeds. So there's, if you type in Northern Powerhouse Rail into Google, that I think that's really the terminology for what we class as HS3. Next question. The diaphragm of the TBM shows some large bentonite tanks. What is the bentonite used for here? So bentonite used for temporarily filling the void. The TBM head is larger than the actual what the segments get installed. So there's this annulus void behind the segments that is temporarily filled with bentonite to support the ground. And then that gets replaced with a grout that will fill the annulus between the rear of the segment to the ground. So it's a temporary use at the TBM head. The time frame for the Manchester Tunnel. I'd nearly put a slide in for that. So Manchester tunnels are going through consultation at the moment. And then we need to go for a hybrid bill, as we did on phase 1, which would be, I believe around 2023, 2024. And I think construction is planned between 2035 and 2040 is the opening. Has COVID set back the schedule? So obviously, yes, we've all had to adapt to new working methods on site and workers in the office. So all of our schedules are constantly reviewed. So I wouldn't say majorly that they've done very well to keep to programme currently, but going forward, we'll have to wait and see to see the long-term effects of COVID. What happens to all the spoil from the building works I've previously answered, that they get reused as structural fills or environmental fills along the route as much as possible. How much bentonite is used? Well, that is obviously for the annulus around the back of the segments. I think the annulus is around 100 millimeters, 4 inches or so. So times that by the circumference of the TBM over the length of the segment, which is a 2 meter long segment. So fairly low amounts. Next question, when is the expected completion date of the tunnels and how long after will the fit out take? I don't have a actual program. I think the completion is planned for between 2027 and 2032, from memory, that is. The tunnels developed varying times throughout the next few years. Obviously, we were shown the first ones are in 2021, go through to 2024. I think the last of the phase 1 tunnels are constructed in London. They're the last ones, but 2021 is the majority of the northern tunnels and the Chiltern tunnels. Into 2022 are the majority of the tunnels being constructed. When you tunnel through coal seams, do you treat the coals as spoils or can you extract it for further use? Obviously, again, depending on quality. Obviously, a lot of the coal seams are with the much more northern tunnels, which are still in their development phase, and we still need to get a lot more ground investigation. So the sooner we get about ground investigation, those sorts of answers will be answered in due course. What degree of reuse of spoil will be possible within the project? Again, we have a whole team of geotechnical engineers that deal with this kind of question. I'd like to give answers, but there is a large percentage that needs to get used on the project because otherwise we couldn't manage. But if there is excess, it's used in various locations like filling old quarries, etc., near to the route. Are there any current sites where the construction can be viewed from public areas from the Chilterns? I'm sure there will be. Obviously, a lot of people like to view these projects. So I believe the best thing is to either look on the local pages of HS2. With HS2, we have various websites called In My Area, and you can look up your own area and get in touch with the engagement executives from those areas who will be advised about the appropriate ways to view the project, and that will be developed over time. What happens to the TBMs when the job is done? Do they move on to the next phase? So obviously a lot of our TBMs are specifically designed for the section they're working on, i.e. the Chilterns Tunnel are the largest, so we don't envisage having any 9.1 diameter TBMs along the route. in phase 2B, so obviously those might not be able to be reused, but considering that's the longest tunnel, they're most probably not in a condition to be reused. They need an extensive refurbishment. But where possible, like the shorter tunnels in the West Midlands, we'd hopefully be able to reuse them dependent on the ground conditions, because there's 3 different types of TBM we can use: an earth pressure balance, a variable density, or a slurry. So if a job in the north, the ground conditions required, which we use in a variable density in the West Midlands, yes, we'd more than likely reuse that TBM in the north, should the programme suit with when that TBM is required. We can obviously send it back for refurbishment, and then if it could be just the head that needs to change, because the heads will be designed specific for the section of tunnel they're working on. Why is the Euston Cavern made of a series of tunnels, not just sprayed walls? So it's mainly due to the size. By splitting up the cavern into smaller chunks, we can reduce settlement. So even if we didn't do these small drifts, we would still be splitting up the cavern into sections, which we call a sidewall drift. So if you've heard about any of the tunnelling on Crossrail, their caverns were about 12 metres tall, and they had a sidewall drift on one and a double sidewall drift on another. Unfortunately, we're slightly bigger than that, and we're next to complex infrastructure, as I noted earlier. So by having these series of tunnels, it reduces the settlement to much more controllable limits to allow the works to be undertaken safely. If you look at where those other tunnels on Crossrail were undertaken, they would have been undertaken underneath a lot less urban area that allowed that method. Will the TBMs be recovered at completion? Yes, all our tunnel TBMs are going to be recovered at completion. There's none that are planned to be buried to date. There's an opportunity to take them out at the North Portal. I think on the last major infrastructure project, Crossrail, there was only 2 that were actually buried. But bear in mind, burying means removing 99% of the TBM anyway. All that's left in is generally the cutter head and basically a can that's left over the actual shield part of the TBM. Where is spoil being disposed of? As I've mentioned, along the route as much as possible. I think I've already mentioned the bentonite for being used for behind the tunnel segments. I've already mentioned the TBMs being reusable where possible. Did I see a pressure vessel in one of the TBM videos for the operators? Yes, so that's for the head. So where the head is, there's a chamber that keeps the tunnel to pressure, and if there's an intervention required to, i.e. change tools, the cutter head tools under pressure, then there'd be a requirement to enter the pressure vessel. When is the expected completion date of the tunnels, and how long after will the fit out take? So obviously all the tunnels, as I mentioned before, are completed various times throughout 2022 to 2024, and the fit out will take us up to the opening date of is it 2032, I think. I'd have to check on that, but that's available on the HS2 website. Where is a huge amount of spoil sent from the Chiltern Tunnel? So I believe that's along the line of the route as well. Obviously, that's more competent material to be used as a structural fill for the embankments. When do you think I'll estimate reaching Manchester? So Manchester comes under phase 2B, and that is in its development phase now, ready for going for hybrid bill, as I mentioned. I hadn't realised how many individual tunnels there were. Are the TBMs reusable or one-offs? And we've answered that. So mostly they'll be reused as and when allowable. And once we get the ground conditions for phase 2B, we'll be heavily looking at the TBMs that have been designed by then, bearing in mind we've only fully designed 4 of the TBMs, the 2 Chilterns ones and the 2 for Long Itchington and Bromford. The others are still under development. So once we know what those TBMs look like with the cutter head, which is the main component for getting through the different type of ground, whether they can be reused on the phase 2 ground conditions. And do you expect to hit any coal seams at the northern end? So yes, going into Leeds, certainly there will be some coal seams and some works that will be required on the coal mines in the northern region. But again, that's under development, and we're heavily looking into those ground conditions at the minute. Okay, thank you. Hopefully.
Okay, Andy. Well, I hope you can hear me. Can you hear
Yes.
me?
Yeah.
On behalf of Subterranea Britannica, fascinating presentation. I think everybody else enjoyed it. I've seen lots of thanks coming up on the chat column here. So
Lovely.
thank you very much. I'm going to have a large drink now if I was you.
Thank you. I hope you found it all interesting, and hopefully maybe sometime in the next few years come back and give you an update maybe.
That'd be wonderful. Thank you.
Yeah. Thanks.
Good night, everybody. Stay well.